importance of population size. Better? At the importance of population size, and specifically how population size affects the evolution of aging in small populations. And Kim talked about this already a bit yesterday, about how we get the evolution of aging. And what I always like to give as an example for that is from Peter Medavard's 1952 paper, where he said to imagine a lab that starts running, and so they order a whole set of test tubes. And then each month, as they're doing experiments, some of those test tubes drop and break, and then you have to order new test tubes. And so what you end up with is, over a couple of years, is an age distribution of test tubes. Or actually, the majority of your test tubes are ones that you've ordered more recently. And you can think of that the same way then for a population of individuals. You can think of a human population actually that doesn't age, where you had an 80-year-old human that looked exactly the same and was just as fit as a 20-year-old. But still, what you would have is that the majority of the population would be younger individuals, just because your probability of being around at age 80 is less due to cumulative mortality. And this is important because what this means is that these younger individuals are actually the ones that are contributing more to population growth, which puts a selection preference towards these individuals. And so then we can also think of a selection coefficient being roughly correspondent to this curve, where here we have much less selection pressure going on. And we can then think about two types of mutations evolving under this scenario, where we have some mutations that we call mutation accumulation mutations, and the classic example for this is Huntington's disease, which has an onset after age 40, and this is basically post-selection. And the other class are antagonistic pleiotropic mutations. These are more classical positive mutations in early life, but then they carry with them a deleterious effect later in life. And as biologists, we can probably think of a ton of those, but the most classic example is tail feathers in birds, where this has a selective advantage early in life, but then those ones later in life with the longest tail feathers then have a more selection against them by predators than ones with shorter tail feathers. And what I want to talk to you about today is how population size is then important within this framework. So we can think about selection, which is always then affected by population size. So smaller populations have reduced selection pressure, or selection is less efficient in smaller populations. But this is compounded then at older ages. And I think the easiest way to think about that is to look at the effect of a deleterious allele. And generally we say that a mutation is invisible to selection, or a mutation is, well, drift is more important than selection when the selection coefficient is much less than 1/2 times the effective population size for a diploid population. And so here I'm showing this now for an extreme scenario where actually we're looking at a lethal mutation. And this is the point at which the selection coefficient then is actually equal to 1/2 times the effective population size. And so then now I've just taken what I showed you before with the different age classes and the selection coefficient, but there, that was just the selection coefficient, and now this is the log to make a linear relationship. And then I'm just plugging in 3 different NE values into that formula to show the effect of the lethal mutation. Okay, so at an NE of 1,000, if we plug that in, we get a selection coefficient of 0.0005, which is all the way out here, so it's an age class around 27. Shifting down to an NE of 100 now, it's a selection coefficient of 0.005, age class around 20, and then all the way down to 10, this brings us to a selection coefficient of 0.05, showing that this is actually shifting this to earlier age classes with reduced population size. That's of course an extreme example, but it shows the basic idea. So then what I did was to look at this in the natural populations. So actually what I'm personally interested in is how lifespan and aging evolves across the tree of life. But to look specifically at the role of population size, it's much more helpful to look at one species, because we can remove out all the other confounding factors and reduce the evolutionary time scale. And so what I'm going to show you now are results from life history of Daphnia populations. So what I did was to go out and collect Daphnia from across Europe and Scandinavia that occur in very different population sizes. What I'm going to show you now, though, are results for genetic diversity as a proxy of effective population size, as that's a better estimate of effective population size than census size. Right. So here now you can see the results for the life history data for those 8 populations. So each of these dots is one of those 8 populations, and here you can see the genetic diversity ranges quite widely. And here are then the life history parameters. So I collected those Daphnia, and then I ran standard life table experiments in the lab and just recorded their parameters. And what you see right away is this relationship between age at death and genetic diversity. So the Daphnia from the larger populations really live much longer than those from the small populations. And the relationship with reproduction was not very big, but there was a negative relationship with age at maturity and a positive relationship with offspring size. And basically what this shows is that the small populations are less fit. So they live less long, it takes them longer to reach maturity, and then they have a smaller size and presumably smaller quality, reduced quality. But lifespan is not aging, and so here you see the survivorship curves now for these 8 populations. In light gray is the smallest population up to in dark black, the largest population. And this then transferred over for log mortality is really the parameter of aging. So generally we say that aging, at least demographically, is represented as increased mortality with age. And then the slope of log mortality gives us the actual rate of aging, or Gaufford's B. And here I've grouped the 4 large against 4 small for simplicity, and then you can see the slope of the dotted line is steeper than that of the solid line, showing that not only do the small populations die sooner, but actually they're dying faster. Okay, and then to see if that fit with evolutionary theory, we then expanded upon the definition of the selection coefficient to include an idea of a metapopulation, where we use Charles Worth's selection coefficient being equal to the relationship with mortality and this theta value, where theta traditionally represents migration and mutation with different mutational models. And here we include then a metapopulation model to look at evolution in differently sized demes. And here you can see the results for several of these demes, looking now again at this log mortality that I showed before, with the solid line being the largest deme, and this the smallest deme, showing again this steeper curve and faster aging in small populations. And then just using a simple formula to equate that over to genetic diversity and lifespan to similar results as for the Daphnia, to show that increased genetic diversity also leads to an increase in average lifespan. Okay, and then to look at what is the genetic basis of this, we performed crosses for these 8 parental populations that I showed you before, where we then inbred them or outbred them in each case. And then the difference between the parental and the inbred is then the inbreeding depression, and outbred and parental is the hybrid vigor. You can also think of an optimum genotype here as a mutation-free genotype, and this difference is then the genetic load of the population. I'll come back to that in a second. And here you can see the results of that for these 8 populations. Again, here I've grouped the 4 small and 4 large. And here's the parental in the small and the inbred. They're basically pretty similar. And here's the outbred, showing a large amount of outbred fitness increase, and this is age at death or lifespan. And in the large populations, we actually see the reverse pattern, where there's a large amount of inbreeding and basically no hybrid vigor. And the cool thing here is that this really shows that if you inbreed these ones, you get the same as in the small populations. If you outbreed the small populations, you're getting that in the large one, really showing that this is a rescue phenotype. And that's important because it shows us this wasn't actually local adaptation between these different populations, but truly due to genetic load. And that's what you see here. Is the relationship between genetic diversity now and the genetic load for age of death, really showing that these small populations are carrying a higher genetic load, and the larger populations a reduced genetic load. And this is important because it really shows that the genetic basis that's driving this are classical inbreeding mutations. These are primarily small deleterious recessive mutations. And it's also important to say with that reduced population size and inbreeding are not in fact the same thing. It's not like the Daphnia are going looking for a more similar Daphnia in the pond together. It's really just that they have such a reduced population size that they become inbred in a way over time, or have reduced genetic diversity and thus increased growth. And collaborator Dan Levitt of the NPI for demography, and all people in my group have my funding sources. And you?
I wonder, are some populations buffered? They may be small, but they have like a dormant egg bank or whatever, so their genetic diversity is buffered despite their actual numbers being relatively small over time. Is there variation in that?
So these populations generally don't have much of an egg bank dynamic going back in time going on. Some of them certainly do, and there is resurgence of older genotypes going on in the ponds, but generally, these aren't like the large populations in ponds we're thinking about for Galeata or Pulex. These come in small rock pools that have a rock bottom, and you can't do sediment cores or anything like that. But certainly there is a bit of resurgence. Yeah?
I don't know if you said this, but do you know if you can actually measure the effective population size or not seeing inbreeding? Do you know if you can actually look for an effective population size of the data to
Like
see?
by measuring the actual census population size and taking the harmonic mean, or?
Oh, just not see the effects of the inbreeding? Or is it just small population versus large population?
Oh, it's just population size. So like I said, they don't intentionally inbreed or something.